Good morning, everyone, and welcome back. In our previous session, we laid the groundwork for open channel flow. We talked about the steady and unsteady flow, uniform and the varied flow, and we also introduced the king of all parameters, which is a Froude number, which told us whether a flow was subcritical or supercritical. But at the heart of all those classifications was a single fundamental idea, the existence of a free surface. And what is the most distinctive behavior of a free surface? It's not just it's there, it's that it moves, it distorts, it forms waves. Now think about it. The surface of a lake is seldom a perfect mirror. It's usually covered with an ever-changing pattern of ripples and swells. Some waves are barely there, others are towering monsters. Some are short and choppy, others are long and rolling. This wave motion is the signature of a free surface, and understanding its basic properties is essential before we can analyze things like hydraulic jumps or flow over a weir. Today, we are going to focus entirely on these surface waves. We will answer two fundamental questions. First, how fast do they travel? And second, what does that speed mean to our Froude number? This will give us the physical intuition we need for the rest of this particular topic. Now, let us start with the most basic question: what is the speed of a simple wave? To answer this, we walk through a brilliant thought experiment. We are going to look at this particular figure. Imagine a perfectly still horizontal channel of water. At one end, there is a wall. Now we give that wall a sudden small nudge to the right with a speed of delta V. This disturbance creates a single small wave, a little hump of height delta Y that starts moving down the channel. A stationary observer on the bank sees this wave traveling with some speed, which we call as c. Ahead of the wave, the water is still. Behind the wave, the water is now moving slowly at that speed delta V. So this is an unsteady flow for our observer on the bank. The river water depth at their feet is zero. Then the wave passes and suddenly they have flowing water. It's changing with time. But now here is the brilliant trick. Imagine you are an observer moving along the bank at exactly the same speed as the wave C. What do you see? To you, the wave profile is stationary. It's not moving. It's just sitting there. The water on your right appears to be flowing towards you at a speed c, and the water on your left appears to be flowing away from you as at a slightly slower speed, which is denoted as c minus delta v. So by shifting our perspective, we have transformed an unsteady problem into a steady one. This is a powerful tool in fluid mechanics. Now, with this steady picture, we can apply um, our old conservation of mass and momentum terms. We draw a control volume that straddles the wave. Let us assume the channel has a constant width b over here. So firstly, the continuity equation as represented by this equation that goes in must comes out. What goes in that have to come out. So the mass flow rate into the control volume from the right is rho times c times y plus delta y times the width b. The mass flow rate out to the left is rho times c minus delta v times y times the width b. So setting them both equal, and we can also rearrange them, expanding and simplifying it, remembering that the delta y is very small, and we can get our first important relationship, which is given by this equation as c is equal to y multiplied by delta v divided by delta y. So this tells us that the wave speed is proportional to the depth and the ratio of the velocity change to the height change. Now we have one question, but the two unknowns, which is the c and the delta v terms. We need another equation over here. That is where the momentum equation comes into play, which is written over here. So we look at the forces on the same control volume. Now, what are the forces? They are the pressure forces, and because the flow has a free surface, the pressure distribution is hydrostatic. Now, remember from our last discussion, the pressure increases linearly with the depth. The force on the vertical face is the pressure at the centroid times the area. Now, on the right hand side of our wave, the depth is y plus delta y, so the hydrostatic force F1 pushing to the left is half times gamma times the y plus delta y whole square times the width b. On the left hand side, the depth is just y, so the force F2 pushing to the right is half multiplied by the gamma multiplied by y square multiplied by b terms. Now, the net force in the direction of the flow, which we will define as to the left, is F1 minus F2. This net force would must equal the rate of the change of momentum. The momentum flux out of the control volume to the left minus the momentum flux into the control volume from the right. The mass flow rate denoted as m dot is rho bcy. So the momentum equation becomes as denoted over here, as written over here. So notice the velocities are relative to our moving observer, and the right hand side simplifies to something. We then later on plug in into our force expressions, and we cancel the term b and expand the term y plus delta y whole square, which and also by subtracting leaves us to the simplified equation as half rho g 2y delta y equals to minus rho cy into delta v. Now we cancel the density term, the y and the factor of 2, then which gives us even simpler equation as g delta y equals to minus c delta v. Now this is interesting. It gives us a negative sign, which is just telling us about the direction. If we think in terms of the magnitudes, we can write the delta V divided by delta Y must be equal to G over C. This is our second relationship. Now, for the grand finale, we have two expressions for delta V over delta Y, from one from continuity and one from momentum, as we have already discussed. So if the left hand sides are equal, the right hand sides must equal. So cross multiplying it and therefore simplifying our final relationship, we can get c equals to under root gy. So this is a beautiful and profound result. It tells us that the speed of a small simple wave depends only on the depth of the water y and the acceleration due to the gravity g. It does not depend upon the wave's height delta y, and it also does not depend upon the fluid density. A tiny ripple and a wave twice its size in the same depth of water will travel at the same speed. So this is the fundamental wave speed equation, and it's the speed at which the disturbance travels, and it's the c variable that forms the denominator of our Froude number, which is Fr Froude number equals to V over C equals to V over under root Gy. So the Froude number truly is the ratio of the flow velocity to this natural speed of information travel on the water surface. Now, you can derive the same equation using the energy and continuity equations. Both paths lead to the same elegant result. Now, our derivation was for a single solitary hump, but what about the complex rolling waves as we see on the ocean? Now, here we introduce the concept of sinusoidal waves as it is displayed over here with in the figure. By combining the sine waves of different wavelengths, lambda and amplitudes, you can easily describe incredibly complex surface patterns. For these more general waves, a more advanced analysis gives us a more general equation for the wave speed as this equation is describing. So look, this looks very intimidating, but it's powerful also. It tells us that the wave speed depends not just on the depth y, but also on the wavelength lambda. The function tangent hyperbola, tangent h, tan is the hyperbolic tangent. But the beauty is that this equation simplifies to our simple under root gy in two very important limiting cases. Look at this particular figure. There are two scenarios. The d water or the short wave case, where y is very greater than the lambda, and the second one is displaying the shallower water or the longer wave case where y is very less than the lambda. Now I would be explaining both of them one by one. Firstly, the deep water or the short wave case in which y is very greater than lambda. So this is when the water depth is much greater than the wavelength. Think of the ocean swells in the middle of the ocean. The waves are long, but the ocean is even deeper. In this case, tangent hyperbola function approaches 1, and our equation simplifies to c is equal to under root g lambda divided by 2 pi. So the wave speed now depends upon the wavelength and not the depth. Longer the waves travel, longer waves travel faster. But when we talk about the shallow water or the longer wave case where y is very less than the lambda, this is when the water depth is very small compared to the wavelength. This is typical for the open channel, the rivers, and for a very special type of the wave called as tsunami. In the open ocean, a tsunami has the wavelength of hundreds of kilometers, but the ocean depth is only a few kilometers. The depth is much smaller than the wavelength. In this case, the tangent hyperbola function approximates its argument. Tangent hyperbola x must be equal to x, and the equation simplifies right back to our old equation as c is equal to under root gy. So this is why tsunamis are so fascinating and dangerous also. In the deep ocean, they are shallow water waves. They travel at immense speeds. So we say that if the velocity is in the range of 500 to 1000 meter per second for the 2004 Indian Ocean tsunami, a ship might not even feel them pass because their height is very small. But as they approach the shore region, the depth decreases and so does their speed also. The wave behind them is still coming in fast, so the water piles up, compresses, and can reach the heights of 30 meters or more. It's the same physics, just in a different depth regime. Now, connecting all of this back to the Froude number, this brings us the full circle right back to the Froude number over here. Let us think about our moving observer again. But this time, imagine the water in the channel is flowing. We have our wave, which always travels at the speed c relative to the water. If the water itself is flowing to the left with the velocity v, what does a stationary observer on the bank would see? There are two scenarios. that the wave traveling to the right or the downstream will appear to move at the speed c minus v. And the second scenario is that the wave traveling to the left, which is the upstream, will appear to move at the speed c plus v. But what if the flow is to the left and is very fast? If velocity capital V equals to the small c, then the upstream traveling wave has a speed of c minus v equals to 0 relative to the bank. It's stationary. But if v is greater than c, then c minus v is negative, and the wave that wants to go upstream is actually being washed downstream. So this is the physical meaning of the Froude number. And we can further say if v is velocity is less than the c, the Froude number is less than 1, a wave can travel upstream, the flow is subcritical. Upstream locations are in the hydraulic communication with the downstream disturbances. But what if the v equals to c? This is a scenario where Froude number equals to 1. A wave attempting to go upstream is stationary. The flow here is critical. And the last scenario is where the V is greater than C. Here, Froude number is greater than 1. And we can say that the wave cannot travel upstream. It's swept away. The flow is supercritical. Upstream has no idea what's happening downstream. So the seemingly simple equation C is equal to under root gy is the bedrock upon which the entire concept of Froude number is built. It's not just a definition, it's a direct consequence of the physics of gravity and wave motion. Now, concluding all of this discussion in this particular lecture, today we took a deep dive into the heart of the open channel flows. We derived the speed of a surface wave and saw that in the shallow channels we care about the most. It's simply c is equal to under root gy. We saw how this speed, wave speed, governs the behavior of the flow through the Froude number, determining whether the disturbances can travel upstream or are swept away. So this wave speed, which is denoted as c, small c, is the fundamental speed limit for information on the water surface. It's it defines the character of the flow actually. Now, armed with this understanding, we can start to look at the energy of the flow. If we have a wave, we have kinetic energy and potential energies also. How is this energy distributed? How does it change with when the flow speeds up or slows down? This leads us directly into our next topic, which is about the energy concentration considerations and the incredibly useful concepts of specific energy. So we will see how the total energy of the flow can be plotted against the depth and how that diagram reveals the conditions for critical flow and helps us analyze the changes in the channel bottom. Our work on the wave speed today produces and provides the physical foundation for the energy concepts we will explore next time. So thank you and see you in the next section.